Okay, so we're working in Chapter 8, and what our end goal is in Chapter 8 is to be able to understand how, or the flow of energy in reactions. And we set up a bunch of sort of definitions of things. We looked at the difference between potential energy and kinetic energy. We also kind of introduced the difference between what we consider heat or energy and temperature. And we also talked about the idea of state functions. And for instance, the most important part about state functions to probably take home is simply that if it's a state function, they're path independent. Meaning it doesn't matter what we do to the system as long as we measure it at the beginning of the process and as long as we measure it at the end of the process, then the change that we care about doesn't matter how we got there. It's kind of like saying if I had a mountain like this, and I'm talking about the distance between point A and point B, it doesn't matter that I have to go up, then down, and then back up. The distance between point A and point B is just a fixed value, right? Now, if I care about how long it takes me to climb the mountain, and I have to go back up, and then back down, and then back up, that's going to be different than if I have a mountain, where I just have A and B, right? Meaning I have to do more work to climb mountain 1 than I have to do to climb mountain 2. I have to expend more energy to climb mountain 1 than mountain 2 because I have to climb up and then I get to go back down a little and then I have to climb back up some of that same distance. So notice that the energy involved and the work involved in a system are not state functions, meaning they're not the best ways to measure it completely. And so what we're going to see is we're going to actually end up combining both of those together in order to think about how to measure those systems. So what we can write then is that if we care about the change in energy of a system, it's equal to Q plus W, where before we wrote that in words and we basically just said that's the same thing as the heat and then any work done. So the total change in energy to a system is simply how much work have we done and then how much energy or how much heat has been exchanged for that. And we said that we have some sign conventions. We said that it's positive if it's endothermic and it's negative if it's exo, meaning things that are positive means that increases the heat of the system or the total energy of the system. So positive things increase the energy of the system. And then for work, we can do the exact same thing. If it's a positive sign, if it's work done on the system or to the system. And it's negative if it's work done by the system. So one thing we have to be very careful of when we're doing these problems and kind of looking at these things is we definitely have to keep track of the plus and negative signs. And I don't know about you guys, but in math, that's what sometimes gave me the hardest problems too, is it's very easy to lose a negative sign. And then what we want to do is we're going to break apart this into two parts. We're going to first talk about the work, and then we'll talk about the heat change in a system. So let's kind of expand on work. And for chemistry, what's the most important type of work is called pressure volume work. Because what we see in chemistry is that we either generate gases, which leads to a change in volume. So the classic kind of descriptor for this is to consider a piston. Gabe, have you guys gotten to pistons in physics yet? Okay. You will, of course, talk about lots of different types of work in physics. We're going to limit it again, like I said, to just pressure and volume work because that's the only thing that matters in chemistry. So if we kind of think about a piston, what we have pushing down on that is pressure. And that pressure can vary. It's usually the atmosphere. And if our system, if the piston is lowered, then that means that we've done work to the system. We give that a plus sign. And if the piston is expanded, meaning it's higher in the container, and I didn't draw very good containers here. Then this is work done by the system. And so we give that a negative value, meaning if I compress a system, that's storing energy in it because they can later be used to do work. If the system is expanding, that's losing energy for it, and that causes the energy change in that situation to be negative overall. And so we can define work in those terms by using the equation work equals minus P delta V. So the minus sign, or basically the minus sign is so that if delta V is greater than 0, it's work done by the system. And if delta V, or the change in volume, is less than 0, then it's work done on the system. And it results in a positive number, and that results in a negative number. And of course, maybe I should refresh minds because it's been a while since we did something. What do we mean by delta V? It simply means the change in. It means the final volume minus the initial volume. So that's just the Greek letter delta, and we simply use it to mean the change in. And we always measure changes as final minus initial, whether we're measuring a change in temperature, whether we're measuring a change in volume, or next chapter we'll also look at changes in pressure. Any change is always final minus initial. So this gives us a weird unit of energy, because if you look at it, work has units of P delta V, while pressure is measured in atmospheres. Now, actually, let's do it this way, minus P delta V. So the units for pressure are atmospheres. Gabe, what are some other units for pressure? Have you talked about pressure at all? Okay, so the other common units are torr, Pascal, and millimeters of mercury. And so you might find that occasionally you have to do a conversion factor. And of course, those conversion factors should be on your cheat sheet if I remember right. And if they're not, I'll put them there for sure. And then of course, volume, what's our normal volume measurement in class? Milliliters. So the SI unit for that is technically liter. But again, if you're given a question with milliliters, or heck, even if you're given a question in gallons, you know, that's just a change, right? And so what that does is that gives us our units of atmosphere liters, or technically we usually say liter atmospheres for whatever reason. I think it's weird. We don't say atmosphere liters, we say liter atmosphere. But the idea is that a liter atmosphere is a unit of energy. Therefore, we have to have a conversion factor for that, and it turns out that 1 liter atmosphere is equal to 101.3 joules. So keep that one in the back of your mind. Again, I need to update my cheat sheet. It's usually what I do for these chapters is I give you a separate little cheat sheet on the test like I did last test. What I really should do is migrate it all to the big cheat sheet so that I don't have to remember to do that every semester. But I always get busy, I always forget what I'm doing, and so I always end up doing it like that. So what we want to think about when we're doing chemical reactions then is the work that occurs when we make or change the number of moles of gas in a reaction. So let's take a look at an example reaction. If I have 2 sodiums and I react that with 2 waters, then I can make hydrogen gas plus 2 sodium hydroxides. And so notice that our states here are solids and liquids. And so we assume that there is no change in volume for those. Or really that the change in volume for the amount of solid that would react or the amount of liquid that react is very tiny. And so here for gases there's a large change in volume. And then aqueous really is just an example of a liquid, so we assume that it's got a constant volume. Meaning, can you really tell the difference between 50 milliliters of water and 50 milliliters of water with a little bit less hydrogen gas dissolved in it? No. The liquids, the density is so hard that it doesn't matter. So we want to calculate the work done at pressure equals 0 and at pressure equal to 1 atmosphere. And I should point out that 1 atmosphere is 760 millimeters of mercury, and that is the standard value. Meaning at sea level, the atmospheric pressure is considered to be 1 atmosphere. Now we're in Rangeley, so what do we know about Rangeley, an atmospheric pressure? A little bit less. And we're not going to be making any of these measurements in lab, so we're not going to worry about it. And so what we always assume is that we're always at sea level. I imagine it's a lot easier to be a scientist at sea level than it is to be a scientist in Denver. You'd have to make lots of little corrections sometimes. And then the other point that we know is that 1 mole of gas generally has a volume of 22.4 liters. And this is an approximation. And it's good enough for what we're doing in class that we just kind of go about it until chapter 9, where we end up doing the actual calculations and we realize that it's not always exactly 22.4, but it's close enough to 22.4 for most things. So in case 1, then, the work is equal to minus P delta V. And so that's equal to minus 0 times 22.4 liters minus 0. And so that really is just 0, which basically is just to illustrate that if there's no pressure, then there's no work. So for instance, if you're in the dead of space and you're doing these sorts of things, there's nothing holding those gas molecules into that container or in a given amount of volume. They can expand to basically infinity. And then, of course, the second case is pretty easy too. It's just W equals minus P delta V equals minus, the atmospheric pressure is 1 atmosphere now, times 22.4 liters minus 0. And that's equal to minus 22.4 liters. And then the idea is that if I convert that to joules, that ends up being minus 2,269.12 joules, or about minus 2.3 kilojoules. So it's a considerable amount of energy. In order to just expand something. Now, note that what this also proves, because whether I'm doing it at 0 atmosphere or 1 atmosphere, is that work, again, is not equal to a state function. Oops. Not equal. And so one of the things we have to realize is that we don't want to use or simply calculate the work for things, because then we have to worry about what path it's being done at, what pressure it's being done at, and a lot of other things. Instead, we want to find something that we can measure that is really a state function. So if we take a look at energy, so we took a look at work, and we realized that we're just going to be using work equals minus P delta V to calculate any pressure volume work. And then we can take a look at the Q. That was our heat term. Now, we're going to, in lab, look at an equation Q equals ms delta T. Oops, delta T. Where this is mass. This is something we'll learn as specific heat. And this is the change in temperature. But we'll save that for tomorrow. And this is lab, oh gosh, is it 3 or 4? I don't know. It does have a pre-lab associated with it, so kind of make sure you read that pre-lab. And we'll go into more detail about Q in lab, so we're going to kind of put that discussion over there. The only thing I want to say is that if we take a little bit of an example, if I increase the temperature of, say, 100.0 grams of water from 20.0 degrees Celsius to 30.0 degrees Celsius at, we'll just say 1 atmosphere, what we should realize is that the amount of heat varies. In that if I use a Bunsen burner to heat it, or if I use, say, a hot plate, or technically, since we're just trying to add kinetic energy to it, if I stirred something hard enough, I ought to be able to increase the temperature of that solution. And so the point I want to make is that Q is also not a state function, meaning it's path independent, or it's path dependent. And so just measuring Q, or just measuring the work, is not sufficient. What we really have to do when we're doing experiments to measure the change in energy is we have to measure the Q plus the W. And this is what's I think is one of those weird things, and maybe it'll also help us think in terms of an analogy. So this is not a state function. This is not equal to a state function. But the combination of them is a state function. So the total change in energy of a system, as long as we're measuring both the work and the heat exchange, is a state function. It does not matter what process we do. If we look at either part individually, then we have to say the process that we're doing. So one of the things we want to realize is that when we're measuring energy changes, we always have to measure both aspects of it. As an analogy, you can think about density equals mass over volume. We said that both mass and volume depended on the amount of matter, right? Meaning, the more I have of something, the bigger its mass is, right? And the more I have of something, the bigger its volume is. But that density does not depend on it. Meaning, the density of a small amount of something and the density of a large amount of something is still the same density, right? Because the density is the measurement, or is the ratio of the two things that depend on matter. And since they both depend on the amount of matter in the same fashion, then, you know, what we generally want to measure or use to identify things, density, does not depend on the matter. Same thing with the change in energy. Even though each individual part depends on the path taken, the total, or the sum of them, is a state function and is path independent. So we can actually measure the changes in energy. Let's see, we want to do more examples or not? Nope, we'll go with that. So we've got our equation. Delta E equals Q plus W. That's the same thing as delta E equals Q plus P delta V, right? Because we know that, wait a second, do I have the sign wrong? Yeah, minus. Because we know that work and P delta V are the same. And so we can write an equation like that. And then we can simply realize is that there's only two cases. So there's only two circumstances that we have to worry about. Circumstances to worry about. Meaning that if delta V is equal to 0, then there's no work done. Or the second case, in which there's constant pressure, in which case there is work done. And so we can take this equation and we can say that there's two separate equations that we can worry about. The first one is delta E equals Q minus P delta V. And if delta V is equal to 0, then that simplifies to the change in energy is simply equal to QV, where that V says that the volume is constant. And this is one of those nitty-gritty things that I sometimes think I should just skip over, because in the end we just pick one of the equations and go with it. The second equation is basically delta E equals Q minus P delta V again. And here we're going to say that this is at a constant pressure, in which case then we can say that Q at constant pressure is equal to delta E plus P delta V. And so this is the amount of heat at constant pressure. Or what it really is it allows work to be done. So we've got two different types of measurements that we can measure of heat. We can either measure heat under constant volume situations, or we can measure heat under constant pressure situations. And it turns out that this is the more realistic measurement. So this is more realistic. And so we tend to make all of our measurements at constant pressures, right? Because what's around us? Does the atmospheric pressure change on the time scale of a normal experiment? Not really, right? But we do normal experiments in beakers. Beakers are open to the atmosphere, so if I generate any gas in a beaker, then that can change. So we have a special name for QP. So QP equals delta E plus P delta V, and we're going to rename that variable delta H. And this stands for enthalpy. And this is one of those things that bugs me. Enthalpy and the amount of heat at constant pressure are the exact same things. So it's two words that mean the exact same thing. And so one of the things that I always found confusing when I first took the class, and also because I had taken physics at the same time I took chemistry, physics was always talking about QP, and chemistry was always talking about delta H. And it took me a long time to realize that QP and delta H are the exact same things. So I don't know, when you start talking about heat transfer and work and all of that stuff in physics, if you're going to, what set of letters you're going to pick in the end.
You use QH and QC for hot and cold, and we haven't even used delta H.
Okay, so you haven't measured the changes yet at all, right?
We have, but it's not with delta H. We've done entropy and stuff like that.
Entropy or enthalpy?
Entropy.
So you've measured the entropy of a system?
Yeah.
So the amount of disorder, right? Yeah, we're going to save that till the tail end of this chapter. So realize that enthalpy is just a fancy way of saying the change in energy plus the change in heat. Or not change in heat, change in the work done. And so it turns out that this also, of course, is a state function. And so we choose to use delta H for doing things because delta H is a state function. Now, the other thing to note is that P delta V means that there's a change in volume, which for chemical reactions means that there has to be a difference in the number of moles of gas in a reaction. So for example, if you have things that's a solid plus a liquid going to say a solid plus a liquid, or you have, two things that are aqueous here and two things that are aqueous here going to something that's aqueous, in a solid, that there's no difference between QP and QV. Meaning if there's no change in volume, if there's no work done by gases, then the measurements are exactly the same, right? And the other reason I think this is a little silly is that if we take a look at a typical reaction, then, let's see, do I have numbers to go with this? I hope so. Where is it? Yeah, I don't see the numbers. Okay, so if I take a reaction like this, where I take, say, C3H8 gas plus 5O2, does anyone recognize the type of reaction this is? So anything plus O2 is, what class of reaction was that from chapter 3 or 4? Combustion. Oh, I'm sorry. You've got to talk louder. I'm way up here at the front of the room. I'm surprised you guys can even hear me. So we always make CO2 plus H2O. And if I measure, and we just said heat or energy. Well, the idea is that now in this chapter, I'm going to replace that and simply say that delta E for that reaction is minus 2045 kilojoules. And that delta H for that reaction is minus 2043 kilojoules. So this is the change in total energy. And remember, energy is equal to Q plus W. This is essentially the Q. And so what that means is that the amount of work done, or the P delta V work, is simply 2 kilojoules. So that's about, what, a 1% difference? And so what we see is that for most reactions, and we'll put this unless large changes in the number of moles of gas, that delta E is approximately delta H. And so for all intents and purposes, we simply use delta H for everything. If we really have to be picky, if we really need to know the true answer, we'll throw in that P delta V work. But that we rarely do something like that. So, and the moral of the story is, despite all the equations we've written down, despite everything that we've looked at, we ignore 90% of it. And so I guess what I really want you to be aware of is that it's there. It's in the back of your mind that it might be important, but that we knowingly ignore it 99% of the time because, I shouldn't say 99%. Well, okay, 99% of the time in real life because there's almost no meaningful difference. And that the only time we ever really care about it is when there's a homework question and one test question on it. So you have to know how to do it, but not worry about it too much. So let's take a look at an example. So I've got the following reaction. Let's see. Where is it? That's not it. Where's my good example? You can't, well, okay, arguably I could make up numbers for something like this, but I never bother to. Oh, I see. I was even super lazy. So I did a silly example like, well, I'll just make one up. That's fine. We can do some work and make it up. So let's say I have the following reaction. I have 2NO gas plus O2 gas goes to 2NO2 gas. And we know that the delta H for this is equal to minus 114.6 kilojoules per mole. And I want to know is how much work is done in kilojoules, because that's our favorite unit, if, oh, and the value of delta E if, say, 200 grams of NO2 react with 100.0 grams of O2, and the reaction, or the change in volume, is equal to minus 60 liters. I'll put a decimal in there to have at least some more sig figs. So notice that on one side of the equation I have 3 moles of gas. On the other side of the equation I have 2 moles of gas. So we expect the change in volume to decrease, right? To be a negative value, meaning we're doing work on the system, right? It's being condensed down. So what we have to realize is that I've got a lot of information in this, right? But essentially the formula that we want to use is simply that delta E equals delta H minus P delta V. And see, we know this. We know this. We know this. Actually, I shouldn't say we know that. Technically, we don't. We have to calculate the actual delta H value for the reaction. And this is also going to realize that this value can be treated just like a reactant or product in a reaction. So what we're really doing is we're taking this equation from chapter 8 and we're going to take our mole-to-mole ratios, our molecular weights, and the concept of limiting reactants from chapter 3. So that's one of the beauties or one of the bad things about chemistry, is that we're always pulling stuff forward and saying, oh yeah, do you remember how to do this? Do you remember that you can't forget chapter 3, right? Not allowed to. So what we're really asking is, can I calculate delta H for that reaction? Well, since I'm given 200.0 grams of NO2 and I'm given 100.0 grams of O2, what that really means is that the first thing I have to do is first find the limiting reactant for that equation. So in order to figure out the actual value of delta H, well, that value is based on moles, right? But do I know how many moles of NO I have? No, I was given it in grams, right? Do I know how many moles of oxygen I have? No, I'm given it in grams. So the idea is that I want to take my 200.0 grams of NO and convert that to kilojoules of energy. I want to take my 100.0 grams of O2 and I want to convert that to kilojoules of energy. So it's sort of our standard problem from chapter 3. What do we always say the first thing we should do in chapter 3 is? If given something in grams, what's always a good thing to do? Go to moles, right? So how do I go from grams to moles? I have to use a molecular weight. So let's see, oxygen is 16, nitrogen is what, 14? Close enough for Jay's ballpark guess. So what does that make? 14 and 16 is 30 grams is 1 mole. And then what's the other thing? If I want to go from moles to something else, so I want to go from moles of NO to kilojoules of energy, so I need moles of NO. The idea is that we know the kilojoules of energy because we're given this equation. It says that if 2 moles of NO react, then I get minus 114.6 kilojoules of energy. And so if I take a look at that, then what I'm really saying is that I've got 2 moles of NO is 114.6 negative sign kilojoules. And if I plug that into my calculator, of course, since I'm making this example up, since I couldn't find the one in my notes, we'll just plug it in. 200 times 114.6 divided by 30 is I make 764 kilojoules. So that's the delta H for that reaction. And then, of course, for a limiting reactant calculation, remember, we've got to do everything twice. And so I've got to figure that I've got what? 16 and 16 is 32.0 grams of O2 is 1 mole of O2. And then 1 mole of O2, oops, check the balanced reaction. Yep, 1 mole of O2 is minus 114.6 kilojoules. And I'm sorry, I forgot the negative sign up there. So 100 times 114.6 divided by 32 is 358 kilojoules with the negative sign. So which one is my limiting reactant? Yeah, my oxygen. So this is my limiting reactant is O2. Therefore, delta H for that reaction is equal to minus 358 kilojoules. Meaning that when I go to this equation, delta E equals delta H plus P delta V, well, I have to plug in what did I just say the value was? Minus 358 kilojoules. Because I didn't have molar quantities reacting, right? And actually, yeah, I did put the minus sign there. Never mind, just making sure. And so then the second part is we got to calculate our P delta V work. Well, the reaction took place at 1 atmosphere, and the change in my volume was what? Minus 60 liters, right? So that's, and then of course, I guess the very first thing I'm going to want to do is convert that to kilojoules. So 1 liter atmosphere is 1 joule, oh, I'm sorry, 101 joules. And then 1,000 joules is 1 kilojoule. And so for that part, I get 60 times 101 divided by 1,000, 6.06 kilojoules. And so what we're saying is that delta E is equal to minus 358 kilojoules plus 6.06 kilojoules. Oops, I'm sorry, this is a negative, because there's my negative sign. So this really needs to be a negative then. And so that is plus 358. I'm really bad, especially when I'm doing things with this, in that I never plug the minus sign into my calculator, and so I always have to remember to put it down. So what that's saying is that the change in energy for that reaction is 364 kilojoules. Or if we look at it, if I ignore the P delta V term, then that's what? 6.06 divided by 364 times 100. That's about 1.7% error. And I got to be honest, anytime you're doing calculations like this in chemistry, if you're within 1 or 2% of the answer, that's pretty damn good. That's well within our tolerances. So realize that the change in energy in the system and the change in enthalpy in the system for chemistry reactions is almost always the same. Very small minor differences if we have a bunch of gases produced. Okay, that should be enough for homework 8B. So we'll get started on the information for homework 8C, but also realize that we're not going to, get enough to actually do anything. So what the rest of the chapter is broken apart into is applications of delta H. And what it really is there's about 6 different things that we can do with delta H. So the first thing we can do is look at delta H of what we call reaction. And that's simply the change in enthalpy for a reaction. That's saying that if I have A plus B goes to C plus D, and I have a delta H value of minus 64, say, kilojoules per mole. So we'll talk about how we can kind of measure that and sort of how we can use that for doing some calculations. But then what we realize is that we don't really want to calculate or measure delta H for every reaction known to man, because that would take a lot of time, right? So instead, we're going to learn a shortcut method where we can approximate an answer using what's called delta H of formation. So this is the enthalpy of formation, which we're going to define as basically making a compound from its elements. So what we're saying is that we can measure the amount of energy in a compound by simply saying that if I've got carbon plus O2 gas, CO2, that if I tabulate these values, so these are tabulated for all elements, then I can calculate anything else that I make, right? Because everything's made up of, what, 110 elements. So if I have a delta H value for all, or a heat of formation value for all elements, then I don't need to calculate or measure it for every known chemical reaction. I can simply make a ballpark measure by using these heats of formation. The third thing we're going to learn about is called Hess's Law. And this is very, very similar to, now I'm going to draw a mental blank. What was the cycles that we did in the last one? The test question that everyone skipped conveniently. Hess's Law, gosh darn it, I'm going to look it up just to make sure I have the right name in there, because it's going to drive me insane if I don't look it up. There's Hess and lattice energy, Born-Haber cycles. It's approximately like a Born-Haber cycle. And what it simply says is that the delta H for a reaction is equal to all the delta H's for the different parts. And so if we can measure a bunch of different parts of a reaction, we can add those parts together to get the delta H for an entire reaction. We're going to look at delta H for phase changes. And what we mean by phase changes is if I go from a solid to a liquid to a gas, or vice versa. Because quite often in a reaction, we do go from a solid to a liquid or a liquid to a gas or something like that. We're going to look at something called calorimetry. That was that Q equals ms delta T. That's what we're going to do in lab tomorrow. And then the last one we look at is something called bond dissociation energies, or I call them BDE, because I get tired of writing it. And this is saying that we can calculate delta H from knowing bond energies. And so what it turns out is there's about, well, here 6 different ways to either calculate delta H for something or use delta H in part of a process for determining or following the heat flow in a reaction. And so these are kind of what I call applications of delta H, meaning we now know what delta H is. It's a measure of it's the sum of the change in energy in the system plus any work. We realize that really we can equate delta H, the change in the enthalpy, with really just the change in the energy in the system. Or really that's mostly measuring the change in the amount of heat produced in a system. Meaning the P delta V part is very small usually. So we have to be careful with our terminology, even though we realize that we play kind of loose and fast with it when we actually start doing all the calculations, because instead of calculating P delta V for every single problem, we just say, let's screw it, say it's about 1% error and not worry about it. So let's do this for the rest of the week. Today is Wednesday. Homework 8A was due. Tomorrow is Thursday. We're going to do lab 3 or 4. It's the one on calorimetry. And then Friday we'll, say that homework 8B is due. And then for next week we're looking at Monday, Tuesday will be lab, Wednesday, and I'm really going to try to put a test on Thursday or Friday over chapter 7 and 8. And I think we can do it. It'll be squeezing it just a tiny bit. So you guys got to stay on top of things. But I guarantee you it's better to have the test before Thanksgiving than to try to remember this over Thanksgiving. Would you guys agree with that at least? It's been my experience that students and myself, frankly, we come back after Thanksgiving, and I'll be honest, I've had times when I've come back from Thanksgiving and I can't remember some students' names. That's how much my brain will shut down over a week break. And then over Christmas, I'll probably forget every one of you. Of course, that might also do with, oh wait, I don't want to put this